In this video, we'll discuss how non-zero vector potentials can lift degeneracies in quantum systems, even if classical fields are zero. We'll start by reviewing gauge transformations and fields, and then we'll do example 4.6, which is the particle on a ring with a solenoid inside. So, the potentials, if you recall, the potentials in classical electrodynamics are not measurable, but they're used to describe fields which are. So the electric field is a function of the classical scalar potential and the classical vector potential A. The same with the magnetic field, it's the curl of the vector potential. Potentials can be arbitrarily changed via gauge transformations without altering the resulting fields, and we showed that in the last video. That is, phi can be replaced with phi prime, which is equal to phi minus the time derivative of the gauge transformation. And the vector potential can be replaced by A prime, which is A plus the gradient of the gauge transformation. In quantum mechanics, potentials are actually an integral part of the Hamiltonian, while fields don't actually have any place in quantum mechanics. Therefore, the Hamiltonian, in the presence of vector and scalar potentials, has to be altered. And you get that H is equal to 1 over 2m times h bar over I del minus QA, all quantity squared or applied twice, plus Q phi. In the absence of a vector potential of electromagnetic fields and electromagnetic potentials, then this becomes the normal minus h bar squared over 2m. The Hamiltonian itself is also invariant under gauge transformation. We showed that as well. Now, up until quantum mechanics, it was presumed that there could be no electromagnetic effects unless there were non-zero fields, because fields acted directly on particles with forces. But in fact, the vector potential can affect the quantum behavior of a charged particle, even if the field is zero, as long as the vector potential exists. So let's consider a charged particle constrained to move on a ring of radius b, enclosing a long solenoid carrying current I, so there's no edge effects. Outside the solenoid, the magnetic field is zero, and the scalar potential is zero. However, the vector potential is not zero, and we can write using the Coulomb gauge, which is del dot A equals 0. In cylindrical coordinates, this becomes del dot A. So it's 1 over r, partial of r A sub r with respect to r, plus 1 over r, partial of A phi with respect to phi, plus partial of A sub z with respect to z, and that's going to add up to 0. In the Coulomb gauge, where del dot A is equal to 0, then you can do that in two ways. One way is to have that the vector potential is only a function of phi. So you only have an A phi component, and that A phi component depends only on variables that are not phi. So we can have this if you have A is equal to A phi hat, and that A sub phi is the flux, capital Phi, over 2 pi r times the unit vector phi, for r is greater than A, where the flux is equal to pi a squared b, and that's the flux through the solenoid. In that case, since there's no scalar potential, the Hamiltonian looks like this. It's 1 over 2m h bar over I del minus q a vector quantity squared. We can develop that and derive the Schrdinger equation for this system when the particle is confined for a ring at r equals b. So we're going to constrain r to be only b. So we only care about the vector potential at r equals b. In that case, we start with the Schrdinger equation, which is the Hamiltonian applied to psi is equal to 1 over 2m times h bar over I del minus QA quantity squared psi, which is basically applying this operator twice to psi. If we now expand this out, we get 1 over 2m, and we get the first term, which is this term squared, which is minus h bar squared del squared psi. Then we have plus q squared a squared psi, that's the second term. Then we have I h bar q del dot a, that's this and this, applied to a psi rather. And then we have I h bar q a del psi. So the gradient of psi dotted into a. And these two are in principle different. And that's all equal to E psi. Now, in this particular gauge where we have del dot A equal to 0, we can take this term here, del dot A psi, and since the gradient is of A times psi, then the product rule says you have del dot A times psi, or A times del dot psi. And del dot A is 0, and so this term can be converted into this term over here, the A dot del psi. Therefore, we have that the Schrdinger equation becomes 1 over 2m times the quantity minus h bar squared del squared plus q squared a squared plus 2I h bar q a dot del applied to psi is equal to E psi. And since psi of r is equal to psi of b, we can constrain the vector potential and del. In particular, we'll have A is equal to the flux over 2 pi b in the phi direction, phi hat direction, and del, all the terms go away except for the term with del, with the del unit vector, with the phi unit vector, and it becomes 1 over b d by d phi. And that's because A, when you take del dot A dot del, the only term that survives is the term that has the phi unit vector. When you make these substitutions, you get the following. First of all, this term here becomes minus h bar squared over b squared d phi squared, because now you only have one variable. This term becomes q phi over 2 pi b quantity squared. And the third term, it gives you I times h bar q capital phi over pi b squared d by d phi. So you have, therefore, if you take the, and multiply by 2m and bring the e over, you get 0 is equal to minus h bar squared over b squared, second derivative of psi with respect to phi, plus I times h bar q phi flux over 2 pi b squared d psi d phi, plus the quantity q squared flux over 2 pi b quantity squared minus 2me, all applied to psi. And we can simplify this a little bit more by dividing by minus h bar squared b squared. So you have just the second derivative of psi with respect to phi. Then you have minus I q phi, capital phi, which is the flux over pi h bar d psi d phi, plus 2m b squared e over h bar squared minus the quantity q times the flux over 2 pi h bar quantity squared. So we start with this, and we now define two constants. One constant is beta, which is q times the flux over 2 pi h bar, and that appears here and here. And then we define, that gives us a simplified differential equation, where now we have d squared psi d phi squared minus 2I beta d psi d phi plus 2mb squared e over h bar squared minus beta squared applied to psi is equal to 0. We now replace this quantity in the brackets with another constant, which we'll call epsilon, which is 2mb squared e over h bar squared minus beta squared. And now the differential equation is simplified, and we can sort of see how it can be solved. So it's d squared psi d phi squared minus 2I beta d psi d phi plus epsilon psi. And you can see that this solution is basically a real exponential, complex exponential. We take the second derivative, gives you a constant times psi, and the first derivative gives you a complex or an imaginary constant times psi, and that gives you this term here. And so if we assume that psi is equal to a e to the I lambda phi, we get a simplified equation which says 0 is equal to minus lambda squared plus 2 beta lambda, because the i's cancel and flip the sign, and then plus epsilon, all times a times e to the I lambda phi. We can ignore the exponential term and realize that this will hold if this quantity here in parentheses is equal to 0. And so lambda can be solved. This is a quadratic equation. Lambda is just beta plus or minus square root of beta squared plus epsilon. Now, you can also have to apply the boundary conditions. And the boundary conditions for this problem are that the wave function at 2 pi, phi equals 2 pi, must be equal to the wave function at 0, or the wave function at any position phi is equal to the same value as any position phi plus 2 pi, because it has to be continuous all the way around. And when we do that, when we substitute that in, phi of 0 is equal to psi of 2 pi, you require that the term up here has to be an integer. That is, lambda has to be an integer. Because when phi goes to 2 pi, you need an integer number of 2 pi to get the two terms to be equal. And consequently, lambda, which then can be rewritten as beta plus or minus b over h bar times the square root of 2me, is equal to n, an integer, where n is 0, plus or minus 1, plus or minus 2, and so on. We can now write down the energy of the system as, from this equation, and backing out all the way through the betas, is h bar squared over 2mb squared times the integer n minus q times the flux over 2 pi h bar quantity squared, where n is equal to 0, plus or minus 1, plus or minus 2, and so on. So the solution with n equals 0 is sort of trivial, because that means there's no complex exponential, it's just a constant. And so there's no direction. But the ones where n is plus or minus 1 and lambda is equal to n, then these can be seen as functions rotating clockwise and counterclockwise around the solenoid. And that means that we now have a degeneracy because of n being plus or minus 1. The energies are different for n is positive and n is negative, which was not the case if you don't have a solenoid in there. The energies are degenerate. But now the degeneracy is lifted by the fact that you have an n is plus or minus 1, because the cross products then are positive or negative before you square them. After you square them, sorry. The solenoid, therefore, lifts the twofold degeneracy of the bead on a ring system, or the particle on a ring system, where you now have Q rotating in the clockwise direction, in the counterclockwise direction, so positive e to the I lambda, has an energy where you have the absolute value of n minus beta squared. And when you have it rotating in the negative direction, you have E sub minus n, which is the same constant, h bar squared over 2mb squared, times the absolute value of n plus beta quantity squared. And you can see that this will have a lower energy than this one. So if the charge is moving in the same direction as the current, then the energy is lower than if the charge is moving in the opposite direction. The energy depends on the field inside the solenoid, even though the field at the particle is 0.